Okay, so thank you for attending. This is Shor's algorithm series, and so Shor's algorithm is the algorithm which actually inspired a lot of research in quantum computing. Um, so when I was in the university, that was a long time ago actually. So I graduated 1996, and at that time, between 1996 and 2000, um, I heard about Shor's algorithm. Um, but during that time, um, I think there was just no. Uh, well, I I saw it in a magazine. It was science. I think it was Nature, and um, there was just not enough resources during that time. Um, yeah, so yeah, hi Ron. Um, yeah, so I did not really pursue it, but during the time I was curious about quantum computing. That was also the first time I heard about quantum computing, and I have a lot of questions that, for example, how do you compute when quantum is probabilistic? So during that time, I cannot really understand, and my focus also was a different part of physics, which is gravitation. So it's entirely different. So now, this course is going to explain to you Shor's algorithm. So I hope that if as much as possible you can attend, because this is going to be a not only one day, but it's actually composed of seven lectures, which we are going to split over 7 days, so 7 weeks, so one lecture per week. And I'm going to give you some exercises so that you will be able to have uh, cemented understanding, uh, just to know if that you understood the content. So there are 7 sessions, and so the first one is about RSA encryption. We need to define that, and we need to know how to encrypt using RSA and how to decrypt, because RSA encryption is among other things the object of this study. So we have an encryption that we want to crack, and so we need to understand what that is. Okay. First, practical, which is session 1. I'll give you a message, and then you encrypt, and then you have to know how to decrypt as well. So that's the first one. The second session is about the theory. So because I will just give you formula in session 1, and then you might be asking, so why does it work? Why does RSA work? It's very important to know why it works, because by knowing why it works, that's how we know how to crack it. No?
Mm.
So yeah, so this is the theory. So RSA, we will discuss a little bit about group theory, because RSA has the same mathematical structure as, from a group theoretic point of view, the elliptic curve. So the elliptic curve cryptography, which is also something that we are going to discuss in this course. Okay, and then so in here in the theory, well, the way we Shor's algorithm is going to crack the RSA is through the period finding. So that's why it's important for us to know what it is. And session 3. So that's why here we have this one here is already talking about RSA quantum computing. Okay, so this one is really more it's really more foundational. So what I mean by that is it's more theoretical. Yeah, so in here we will be mostly dealing with mathematics, which is actually very important in quantum computing. So that's why that's the foundation. Okay, so we are going to do that first before we even go to the actual programming using the Qiskit framework. So in here, we review the period finding, and then we describe how to set up the Shor's algorithm. So what kind of the input register, the output register, and the
Fourier transform mode NLA.
Yeah. So in the so we are going to describe about the superposition. So superposition is very much used here. No? Otherwise, and this one discusses the power of quantum computing, because because of quantum computing we are able to do superposition, and because of that, when we apply quantum Fourier transform, so there's a part there where we do the where we compute for the modular exponent. That's possible. It's possible to do all of them in parallel because of superposition. And to find the period, we need to apply the quantum Fourier transform. And once you get the period, you are going to apply what is known as there's a theorem in the number theory, which for which you can compute the period using the continued partial fraction expansion. So this is the part where you can just use your calculator. So this is the classical part. Okay, so the quantum part is finding the period, and then once you get the period, you can get the what is known as the inverse modulo of the period, which is the one that you'll use to decrypt the message. And finally, we are going to compute the probability of success. So here in if because quantum computing is about the probabilities, so how many times do you have to run your quantum computer, to run your algorithm in order for you to have a high probability of success. So this is so mostly this one is mostly mathematics, but that's okay. Okay, so fourth is the elliptic curve cryptography. So elliptic curve cryptography is being used by it's already commonly used encryption, and the reason for that is with just a few bits you can already it already has the same encryption power as RSA. And that's very important because there are some devices that are low powered. For example, your cell phone that needs to have encryption, and so with the number of bits lower than the RSA, you can encrypt faster, and but still be confident that the the encryption power is almost the same, or of the same strength as the RSA. So that's why elliptic curve cryptography is here. It's also here because fortunately, elliptic curve cryptography is based on geometry. It's actually based on points on the elliptic curve. And the reason why it's here, being discussed alongside with RSA on Shor's algorithm, is because from a group theoretic point of view, they are similar. Okay, so the both of them are instances of what is known as the hidden subgroup problem. Okay, so the hidden subgroup problem is the one that's that the Shor's algorithm can decrypt. So that's why it's here. So I mean that's fortunate and unfortunate. Okay, so fortunate because Shor's algorithm is powerful. Unfortunate because if we have already a quantum computer, it can decrypt it, so it will decrypt our standard algorithms that were being used right now in the in the e-commerce. Okay, so here we're going to just in session 4, I'm just going to discuss to you the mathematics, the geometry of elliptic curve. Okay, so there's nothing quantum here. So we're going to discuss also the group structure. Okay, and then and how do you encrypt using elliptic curve, and how do you decrypt? Okay, session 5, in here we are going to show that, well, Shor's algorithm can actually decrypt elliptic curve. How? By showing that it's it's the same as you use the same technique, which is to find the period. So once you know how to find the period, you just put it inside a quantum computer, run Shor's algorithm, and then you should be able to follow the same pattern as how you decrypt the RSA. Okay, but here there's no we don't do any partial fraction expansion. So this is much more straightforward here. And number 6 is lesson number 6. This is where we introduce now the quantum Fourier transform. So so we define first what it is, and we are going to also discuss the Fourier transform that you use in in ordinary in classical computing. It is used in what you call this, the digital signal processing. So yeah, so we discuss that, and then we give a example of we start small. We give a 2-qubit example and how it looks like. Okay, and then here we discuss about the Hadamard gate and the controlled phase rotation. Okay, so these are the 2 gates which we are going to use in building the circuit for the Fourier transform. And then we are going to derive the general circuit for a quantum Fourier transform. And from there, we are then going to construct a circuit for a 4-qubit system. Okay, so and this circuit that we are going to use, that we're going to create for the 4-qubit system, is then the one that we will use in the final session, which is really doing this in the programming it in QISQ. Yeah, so from here you can see that we'll do a review of RSA again. So we'll just be doing RSA, and then we're going to design the modular exponentiation circuit particular to our problem, and implement the Fourier transform in Qiskit. And then we then run it and visualize the output and compute the period and decrypt the message. And that's it. So by the end of the session 7, in fact, this is the most practical, probably the most practical in terms of there's only a minimum of mathematics here because we already covered all of it in the preceding lecture. So this one here, it's you will see mostly the Qiskit. So that's which is good. I think by session 7 you will. From my experience with Asher and this Lester, the feedback I got from them is it was actually in this last session where they were able to connect everything. So this is the outline. Okay, so now let's proceed with the session number 1. Okay, so let's learn about RSA encryption, and let me get the RSA encryption here. Let me just transfer this and this one here. Okay. This single page. Okay. So let's start with motivation. Okay. So encryption is really all about being able to send a message to someone in such a way that it is secure. There are many encryption systems, and probably the most basic of them is known as the Caesar cipher. Okay, so what you'll do is you just shift the letters. For example, if you want to send a B, you actually send a C. And if you want to send a, for example, O, you send a P. Okay, so BO, so CP. So that's the Caesar cipher that was used during the Romans, the time of the Romans. Now, so in encryption world, there are 3 characters. No? So, well, there are 2 main characters. Alice and Bob, and there's a third one actually. Her name is Eve, so the eavesdropper. So when Alice wants to send a message to Bob, she would like to use a symmetric cipher. Okay, so a symmetric cipher. So you have a key that both of you, both Alice and Bob, know, so that because that's the one that they are going to use to encrypt messages to each other. And the reason why symmetric key is they want to use symmetric key is because it's faster in terms of when you encrypt something, it's faster to do it using a symmetric key. But the problem of using a symmetric key is that if someone like Eve, an eavesdropper, is able to intercept your symmetric key, then she can also use that key to decrypt. Okay, so the message. So that's the symmetric key is the one used to encrypt and decrypt. Okay, so there's only one. Now, so how do Alice and Bob use a symmetric key for encryption, but then be able to tell each other, okay, we'll use this, but still be protected from the eavesdropper, okay, which is Alice. So what they'll do, this is where you use now the asymmetric, so asymmetric key. The reason why it's called asymmetric key is because you have two keys. Asymmetric encryption, because you have two keys. One key is for the encryption, which is called the public key. Okay, because the way you call it public is because you can just you have to announce your key to the whole world. If someone wants to send a message to you, they can just get your public key and encrypt the message and send the message to you, because you are the only one who can decrypt that information, because you're the only one who knows the private key. So RSA is a asymmetric encryption, and it uses a public and private key, and it is based on the factoring of large numbers, the difficulty, okay, the hardness of the problem of factoring large numbers. Okay. Okay, I'm done with that. Yeah, so with RSA, you have two large numbers, P and Q, and then their product is N. Okay, so let me just here, N. Now, there is another number, E, which you will use to encode the message. Okay, so it's a number we use to encode the message. And the numbers N and E, they're called public key. But it's a set. So and that set is called a public key, because you have to announce this, you have to publish this, okay, somewhere, so that anyone who wants to send a message to you, they will just use that. And then, yeah, so Bob will use this to encrypt the secret. Okay, so how do we create? So given a message, we know that messages are, ordinarily made out of text. Okay, and how do we make them into numbers? So we will have a what you call this, a mapping. Okay, we map numbers to letters to numbers. Well, this mapping is just artificial, because in the actual computer industry, or in our computer, there's really a mapping between numbers and letters, okay, symbols and numbers. It's called the ASCII. It's called ASCII. Okay, so for example, capital letter A is number 65. Okay. But for our particular example, because we just want to use small numbers for this example, we're going to create our own mapping. Okay, so here you can say that it's just a very simple mapping of A up to letter Z and a blank character. Okay, so blank character. And so we don't use commas, apostrophes. All of those things, we're just going to use these letters. And so it starts with 0 up to 25, and 26 is the yes, the blank character. So if we have a message called "this is a secret" message, how am I going to encode this into numbers? Now, using our previous mapping, for example, letter T, that's number 19. Okay, so if we go back to the previous slide, letter T is number 19. Okay, and letter H is number 7. Okay, and so on. Okay, so that's how you do it. Now, if the number is less than 10, we want to pad it with 0. Okay, so that we will have a uniform blocks. Okay, uniform blocks. We want to pad that with 0. So for example, here, number 7 becomes 07, 8 becomes 08. Okay, 0 becomes 00, 4 becomes 04. Okay, so it now looks uniform. Okay, and to conserve space, we can also group these blocks of numbers. Okay, so for example, I can have, instead of 19 and then space 07, okay, you can just have 1907, okay, and then 0818. So that's how I will encode my message. Okay, so once you have that, I will now give you a formula on how to encrypt that message. So I'm not sure if all of you are familiar with the modular operation, but I'm going to explain that. Okay. So let's take a look at this one here. If your message is A, if your number is A, and you have a given number C, to encrypt your message, you just multiply A C times. Okay, so remember, this one is part of your public key, the C and the N. Okay, so if I have a message and I want to encrypt it using someone else's public key composed of C and N, so what I'll do is I'm going to multiply A C times. Okay, so for example, if C is equal to 3, I'm going to multiply it 3 times, like A times A times A, A times A times A, and then get the remainder. And then what I'll do is I'll divide it by N with this one here, and I'll get the remainder. And the remainder is this one, this number here. Okay. So is that so that's the explanation of the modular operation. Okay, so the modular operation is just getting the remainder of this number with respect to this divisor. Okay, so is that clear?
Yes, Sir Bob. My question po ko, Sir Bob.
Okay.
How can we get like the CNN from the public key, sir? How to determine what's like the process of getting C and N?
You don't there's no process of getting it because it's already given to you. That's your public key. It's composed of 2 numbers, C and N.
Okay, sir.
So if you want to send a message to me for example, you can ask me, what's your public key? And I will tell you two numbers. Okay, and then I will tell you, okay, C is this one, N is this one.
Okay, sir. So public key composed of two.
Yeah, two
Okay,
numbers.
sir. Okay,
Yeah.
sir. Got it, sir. Thank you po.
Okay. So what is this mod operation? Okay, so I already explained it earlier. It's just getting the remainder. So if we have 10 raised to the 7 modulo 17, so what we'll do is we just divide it by, actually this should be, okay, 17 is the number. Yeah, so this should be 17. Okay, sorry guys, there's a typo here. Okay, so let's take a look. Okay, so what is this number? Okay, let's take a look at this one. Okay, okay, and then the modulo is this one. Actually, there's a Python. If to get the given a number, raise it to a certain power and get the remainder. This is just this is the what you call this, the function, okay? POW. So POW raised to the 7 and modulo 17. Okay. See? 10 to the 7. Okay. Run it. I think my example is wrong. Okay, so let me just say that we can also do the reverse. So mod 17. So what you can do is let me just give another example. Okay, so this one is an example. This is 10 to the 7 modulo 17. Okay, so let's do this first. Okay, we have this 10 raised to the 7. Okay, actually this is the same thing. Okay, so it's different. Okay, so this one. Okay. Okay. And then, if you want to get the remainder, just do this. Okay. 17. Okay, so I got confused, no? Because what happened to me? I copied this, no, which is already the result of 10 to the 7. So that's why I got the wrong answer. Okay, so it should be like this. Okay, so 10 to the 7 modulo 17. Okay, we can also do this if you. So this one is 10 to the 7. Okay, now to get the remainder, you can just do this. Okay, so that's also a modulo operator. Okay, so it's the same thing. It's just more convenient to do this, and it's also much faster because this one is implemented. This function is implemented natively in I think in C, so that's why it's also it's better to use this than the percent sign. Okay, so that's the mod operator. Okay. Now, so let's now choose numbers P and Q. Okay, so remember the letter N. Okay, so So in our public key, we have two numbers, right? The C and the N. Okay. Now the number N there is the number that is a very big number, which is actually composed of which can be which is actually a product of two numbers. Okay, so N is a product of two numbers, which is P and Q. Okay, so we specify P and Q to get N. Okay, so for example, if P is 53 and Q is 59, and we have a C is 7, then we have letter N, which is equal to P times Q, which is 3127. And then if we encode 1907, raise it to the power 7, okay, multiply it 7 times and get the remainder, we will get 794. Okay, we just pad it with a 0. Okay, so ito yun, no? This is the one. Okay, so 1907 to the power 7 modulo 3127. If you run it, so you get 794. Okay, so we just pad it with 0. Okay. Interrupt me, okay, anytime if you want, if you had a question, because I know that you're not true. Okay. Okay, so now, okay, so imagine guys, now we have all of these numbers, 1907. So where did I get all these numbers? Okay, so this is just our message. Okay, if you go back here, all of these numbers, okay, I'm going to use this algorithm, okay, this to encode it, to encrypt it. Okay, so this is just the Python code for that. Okay, so for N in this one here, we just print the result of this one. Okay, so this is the one here, and I just need to run this. So I have 794, 1832, okay, 1095. So if the number is less than 1000, I will pad it with zeros to the right, sorry, to the left. Okay, so for example, 268 becomes 0268. Okay, and this is what happens. Okay, so 0268. Okay, so what you have here is already your ciphertext. No, ciphertext is also the same as encrypted text. Okay, and this is the one that you're now going to send to Alice, okay, or someone you want to communicate with. This is already the encrypted text. Okay, and only Alice can decrypt this. Okay, unless someone else knows of the private key of Alice, or can, using a quantum computer, get the period and can decrypt this. Okay, but in a perfect world, only Alice can decrypt this message and read the contents. So when the recipient, okay, gets the message, she can decipher it using the private key. Okay, so the private key, which we call D, is the inverse modulo of C. Okay, so the inverse of C modulo P minus 1, Q minus 1. Okay, so earlier we have P and Q, diba? So P and Q were 53 and 59. Okay, so if we do a minus 1, so this becomes 52 and this becomes 58. Okay, so this is what it is referring to. Okay, so D is just the inverse of C modulo P minus 1. So what does that mean? So you get 1 over C and get the remainder. Okay, remainder of that with p minus 1, q minus 1. Okay. So yeah, so it's called a private key. So once you have this letter D, if you have this letter D, then it's very easy to decrypt, no? So what you'll do is, once you get the message B, you just raise it to the power D, okay? And then modulo the N, you get A. Okay. Actually lack something here. So how do you compute for D, okay? To compute for D, this is the formula. Okay, so it's because it's called the inverse modulo, no? It's the reason why it's called inverse modulo is or let's just say the reason why it's called inverse in the first place is because if you multiply C times D, it gives you 1, diba? So any number, for example, C, suppose C is not equal to 1, and if you multiply it by a number D not equal to 1 and give you a 1, then you can say that both of them are inverses of each other. Okay, that's why it's called inverse. But it's inverse modulo because you're actually getting the remainder. Okay, so C times D modulo. So if C times D modulo P minus 1 Q minus 1 is equal to 1, then you can say that C times D are inverses of each other. Now, since we know C, we just need to compute for D, okay, using this formula. So how do you do that? There's a Python code for that, okay? Well, this is a very inefficient Python code, but it will illustrate the point, okay? So what does this Python code do, okay? So we have N, okay, because we have P and Q, and we have 7, we have C. Now to get the letter D, what I'll do is I am going to enumerate all the possible D's between 1 and this number, okay? And then I am going to multiply C times D and get the remainder. Now, when the remainder is equal to 1, that is the D that I am looking for, okay? So that's the inverse of C. So that's why in here, if x is equal to 1, I'll print the D, which is the inverse modulo, and which is also the private key. Okay, so let's run this. Run 431. Okay, so 431 is D. Okay, so it's 431. So 431 is the private key of Alice, no? So whenever you send a cipher text or an encrypted message to Alice, Alice will just get your message, multiply it to 431 times, get the remainder, modulo this modulo N, okay, modulo P times Q, and the result will be the message, okay, which is a number, and you have to map it back to the letters, okay. So so by using D and applying the formula, so for example, if I sent the message 794 and I raise it to the power 431 and get the remainder, I will get this, which is actually our original message, no? So to refresh your memory, let's take a look. So 1907, is it our original message? And is this our cipher text? So let's take a look. Okay, so 1907 is our original message, and it gives us the 794. So we just reverse the process, okay? So 794, you raise it to the power D. The D is the private key, and then you get this one. Okay, so going back, you get this one. Okay, so that's how you decrypt the RSA if you have the private key. Okay, so if we now apply this to the entire ciphertext, so we have a Python code to do that as well. This one here, okay. So if we run this, okay, you'll get 1907, 818, 2608. Okay, the first three numbers, and then if we go back to our original message, okay, go back to our original message. Yeah, 1907, 081826. This is the original message. And look at that. Okay, so now we have recovered everything. Okay, we have decrypted it. Okay, so it's just a matter of mapping these numbers back to the letters to get the original message. Okay, so using this mechanism, that's how you send your symmetric key. Okay, so now that Alice can send the symmetric key, yeah. So I'm Bob. Okay, I sent to Alice the symmetric key. Alice decrypts it, and from there we both can now just use the symmetric key to encrypt messages between the two of us. Okay, so that's how this works. Okay, now this is the time where we think like a cracker. Okay, think like Eve. Okay, Eve is the eavesdropper, or Eve is some person who wants to crack the message. Okay, that the two, Alice and Bob, have been communicating in order to read it. No? And since Alice is really very she really hides her public key that no one else in the world knows it. There is only one way to be able to decrypt the message without knowing the private key. Okay, and that is by computing the period. Okay, so computing the period. So what is a period? Okay, so in the previous section we learned. Okay, so we have a big number n, and we have C as the encoding number. Okay, so another way, so period finding is like this. So this is the message that you sent to Alice, right? If you know, let us say by some mechanism, you know the period, then you can use the period to decrypt the message B. Okay, but what is the period? So the period is defined as the smallest integer that satisfies this one. So what does it mean? This one means that if I multiply B, okay, the B is the encrypted text, okay? If I multiply it R times and get the remainder with respect to n, and I get a 1, and that we say that R is the period. Okay, so if you have a number R such that